So what we're going to do now is consider, for example, something producing sound while it's moving. So imagine that you're right here, okay, and you have an object over here, and the object over here is actually making sound, okay. And so what we want to do is, as the sound is coming towards you, it's coming at some speed, the speed of sound, okay, and it's got a wavelength here, and it's got a frequency. So we know that C equals lambda F. Okay, but what if it's moving at some velocity v? Okay, I'm going to put a vs to indicate the source of the sound is moving. Now, what happens though now is that while it's sitting here, it's got some frequency f naught, and then lambda naught is going to be the wavelength. But if it's moving, then each wave is moving while the object's moving. So that means that this wave moves over to here, but instead of the next wave starting at the same spot, the next wave starts a little bit closer. So that means that lambda prime, this is the wave that you actually, that this person over here is actually seeing. They're seeing a shortened wave. So the wave is somewhat compressed because of the motion. Well, that means how far did it get compressed? So lambda prime is going to be equal to lambda minus the velocity of the source times the period. Okay. And so now we would say, therefore, that because it's a different wavelength, then what you hear is a different, what you're going to hear is actually going to be different from what the original was. Okay. And so, so C equals lambda prime F prime, because you're going to hear a different frequency because it's a different wavelength. Obviously the speed's going to be the same. Okay, so lambda prime, okay, we'd said was equal to the lambda naught minus the velocity of the source times the period. Well, the period is the F naught, the frequency right here. Okay. And so if I look at this and I want to find, well, what do you hear? Let's solve for that. That's going to be C over lambda prime. So that's going to be C divided by lambda naught minus V sub S over F naught. Okay. Well, if I divide top and bottom by C, that's 1 divided by lambda naught over C minus V sub S over F naught. And so F prime is going to be equal to 1 divided by, well, lambda naught over C is 1 over F naught minus V sub S over F naught, or in other words, that's going to be equal to 1 divided by 1, sorry, there's a C down here because we divided top and bottom by C. 1 V sub S over C times F naught. Now, that would be if the object were coming towards you, and so it's coming towards you, and you got a shorter wavelength, and so the frequency that you hear is going to be 1 divided by 1 minus V sub S over C times F naught. What if it were going away from you? What would happen? Well, what would happen is that now the wavelength is going to be lambda naught plus V sub S times period. Well, remember, this minus sign in the equation up here came from the original minus right there. And so that means that if it's going away from you, then what you get is 1 divided by 1 plus V sub S over C times F naught. Okay. So we can make a general sort of thing here and say F sub S, f prime, what you hear is going to be 1 divided by 1, either minus or plus velocity to source over c times f prime, or times f naught, rather. Okay, that being the original frequency. Okay, now, that's nice, but what if you're moving? So let's say instead the source is sitting here still, and you are moving that way. So you're the observer or the detector. Okay, and so we'll say you're the detector, and so you're moving some velocity v sub d. Okay, and so what happens is that the sound's coming at you with some velocity c. You're moving that way, so it's almost as if the sound's coming at you quicker. Okay, and so what that means is that c equals, again, lambda naught f naught. C prime is going to be equal to the lambda times f prime. Okay, because the wavelength in this case is not changing. Okay, but now the frequency is going to change because the apparent speed changes. So that means if you're going towards it, it's going to be a higher frequency. If you're going away from it, lower frequency. Notice before, if it was moving towards you, it was 1 divided by 1 minus something, so that made it higher frequency. Whereas if you go away, it's lower frequency. Rather, if it was going away, it's lower frequency. Okay, so that means we can look at our equation here. We can plug in for this. Okay, and so we would say that, therefore, we would say that lambda f prime equals c plus vd. Okay, well, if I divide both sides, divide through by lambda, so this is lambda prime equals c over lambda plus v sub d over lambda. Okay, if I multiply top and bottom over here by c, okay, then c over lambda is f naught, okay, plus v sub d over c f naught. So what I have here, f prime equals 1 plus v sub d over c times f naught. Now that would be if you were headed towards the source. What if you're going away from the source? Well, that would change that to a minus. Okay, so we could say that if you're moving, then f prime is 1 plus or minus v sub d over c f naught. Okay, now, what happens if the source is moving and you're moving? Well, it's going to be this combination of both of them. So f prime is going to be equal to 1 either plus or minus v sub d over c divided by 1 minus or plus v sub s over c f naught. Now, you notice this is ever so slightly different from the form that the book uses here. Okay. First of all, I do plus minus and minus plus. Now, why am I using this? In both cases, the upper is moving toward and the lower is moving away. Okay. So toward, away. This is going toward, that's going away. And this is the way I remember this. Okay, and now you can multiply through top and bottom by c to make it look a little bit neater, but I kind of, this works for me. You may use it like this, you may use it the way that does it, but I like to remember it as 1 plus or minus v sub d over c 1 minus or plus v sub s over c times f naught. Okay, and again, the c is the speed of the wave. In this case, it's the speed of sound. In next semester, it's going to be the speed of light. This relationship of the change in apparent frequency that you hear due to motion was actually first studied by Christian Doppler, and so we call this the Doppler effect. The Doppler effect holds for any wave. Okay. And so what happens is, if something is moving, you hear this, you hear the shift as it's moving. If it's coming towards you, it's higher frequency. If it's going away from you, lower frequency. And so if you're standing alongside the road and a car goes by here, then it's going to make a sound. The sound's going to change as it passes you. It's going to be higher frequency here, lower frequency over there. So it's going to sound and likewise, a siren, an ambulance, or fire truck going by is going to be higher pitch approaching you, lower pitch going away from you. In weather, you've got a storm here that's rotating, so it's coming towards you or away from you. You send radar in here, the radar reflects back, and so it goes at one frequency, it's going to reflect off and come back at a different frequency. So in this case, it's higher frequency. In this case, it's lower frequency, and so you can actually look at it. We call this Doppler radar, and you can see, for example, that one side of the storm is coming at you really fast, the other side is going away from you really fast, and that tells you there's rotation inside the storm right there. Police use the same sort of thing. You're driving down the road here, and the cop sends radar, bounces off your car, and comes back, and then if there's too much of a Doppler shift, they pull you over and chat with you about that. And so again, you can work backwards. You know, we found the change in frequency based on the speed. You can work backwards. If you know the change in frequency, then you can find the speed that's moving. And really, the way the cops do this, the way the radar actually does it, is actually even more cool than that. What they do is they have it comes out at one frequency, comes back at a different frequency, and what they do is they mix the incoming and outgoing, and they get the beat frequency, and they use the beat frequency to figure out how fast you're going. And so that's how police radar works, and that's also really how the Doppler radar works also. So that's the basic idea of the Doppler effect.